Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to pick up right where we left off with our discussion on aqueous ionic equilibrium. Specifically, we're going to be talking about acid-base titrations. Very interesting, very exciting stuff. I am on the edge of my seat right now. Can't wait to talk to you guys about this stuff. So without further ado, I present to you Aqueous Ionic Equilibrium Volume 4. As always, your feedback is more than welcome and highly appreciated, so please feel free to drop your questions, comments, concerns, and what have yous in the chat box if you're watching live, or better yet, you can call into the show using Discord. There's a link right down there in the description for you to do that. And if you're watching this as a video, I would appreciate your feedback in the form of a comment. Without your feedback, I am completely and totally lost. So, all right, so we're going to briefly review the topic from the content from Volume 3, and then we're going to jump right into the fun acid-base titration stuff. So, Volume 3, we talked all about buffer effectiveness, right? We're continuing our discussion on buffers. A buffer, of course, being an aqueous solution with significant amounts of both a weak acid and its conjugate base. The function of buffers, of course, is to resist changes in pH upon adding small amounts of acid or bases to the buffer, right? And there are a couple of factors that affect the effectiveness of a buffer, and one of them is the relative amounts of the acid and the base that are in the buffer, and then the other one is the absolute concentrations of the acid and the base that are in the buffer. Relatively speaking, if you want the buffer to be most effective, you want to make sure that the amounts of acid and base are as close to one another as you can. Ideally, you would have a buffer in which the amount of acid is equal to the amount of base, in which case your pH would be equal to the pKa of that weak acid, according to the Henderson Hasselbalch equation. By the way, if none of this is ringing a bell, if you're totally lost on what I'm saying right now, I would highly encourage you to check out my playlists. I have a playlist called Aqueous Ionic Equilibrium live streams, and prior to that, I created a playlist called Acids and Bases live streams. All of that content is very much relevant to what we're talking about today. So like I said, relatively, if you want that buffer to be effective, you need to make sure that the amounts of acid and base are close to one another. And as far as absolute concentrations go, buffers are most effective when the concentrations of the acid and base in the buffer are at their highest. So again, if you want a very effective buffer, what you need to do is you need to make sure the concentrations of acid and base are high and that they're very close to one another, and that will be a very effective buffer. And we also talked about a couple of properties associated with buffer effectiveness. One of them is called buffer range. The other one is called buffer capacity. So buffer range is simply the range in pH over which that buffer can be considered effective. Usually that's the pKa of the acid plus or minus 1. We talked about this in more detail with some examples in the last live stream in Volume 3. And then there's buffer capacity. And buffer capacity refers to the amount of acid or base that can be added to the buffer without destroying the effectiveness of the buffer. So in other words, how much acid or base you can add to the buffer without consuming all of the existing weak acid or conjugate base that's already in the buffer. All right, so that was the content from Volume 3. So tonight, we're going to jump right into the new stuff. So we're going to be talking all about acid-base titrations. So what is an acid-base titration? Well, I've shown on the screen here a typical apparatus that you would use in the event of an acid-base titration. It looks kind of like this, where you have this inverted graduated cylinder type thing with a stopcock and a drip tip at the bottom. That's called a burette. And you have this Erlenmeyer flask at the bottom here. And loaded into the burette, you have a substance called the titrant, which is of known concentration. So this is something that you know it's either an acid or a base, and you know the concentration of the acid or base that you load into the burette. That's your titrant. And then down below, you have what's called the analyte, which is something that you know the volume of, but you don't know the concentration of, right? And notice here the markings on the burette. You have 0 up at the top, and then 10, and then 20, all the way down to 50, right? So this is kind of in contrast to a graduated cylinder, where like if it's a 50 milliliter graduated cylinder, the 50 would be on top and the 0 would be on the bottom. A burette is the opposite, right? So a burette, instead of measuring how much liquid is in it, it measures how much liquid has been dispensed from it, right? So the basic idea here is that you add your titrant to your analyte very slowly. You're carrying out a chemical reaction, an acid-base reaction. You know the concentration of your titrant. You also know the stoichiometry of the reaction, and you're basically trying to figure out how much titrant you need to add to react with all of your analyte. And if you know how much titrant you need to add to react with all of your analyte, and you know the volume of your analyte, well, you can use that to calculate the concentration of your analyte. And this is how an acid-base titration works, and this is how it's performed. And there's another term that we need to be familiar with regard to acid-base titrations, and it's called the equivalence point. So the equivalence point, as the name of it implies, is the point during the titration at which the amount of acid is equal, hence the word equivalence, the amount of acid is equal to the amount of base. And that is determined by either a pH meter, so you'd have like a pH meter probe in there that's monitoring the pH over the course of the titration, or it's monitored by an indicator. I don't know why there's a number 2 there. It's a typo on my part. I'm going to fix that real quick. So a pH meter or an indicator, and an indicator is a substance whose color depends on the pH. So it'll actually change colors when you reach a given pH, and the indicator will be chosen such that it changes color over the equivalence point of that particular acid-base reaction. So in this live stream, what we're going to do is we're going to calculate the pH values along the way of an acid-base titration. So what we're going to do is we're going to set up a scenario in which we're going to be titrating a strong acid with a strong base. Now, I've chosen a strong acid with a strong base because the calculations associated with such a titration are much, much easier than if you have either a weak acid or a weak base reacting with a strong base or a weak acid. So we're going to be doing a strong acid-base titration, again, because the calculations are easier than if you had a weak acid or a weak base. And then maybe in the next stream or something like that, we'll do a weak acid, strong base titration. So basically what we're going to be doing is we're going to be titrating a 100 milliliter sample of 1 molar hydrochloric acid. And switch to this real quick. Hang on just a moment. Yeah, we're going to be titrating a 100 milliliter 1 molar HCl solution with 1 molar sodium hydroxide, right? So HCl, of course, hydrochloric acid, that's a strong acid. Sodium hydroxide, that is a strong base. And what I've chosen to do in this presentation is to plot our values using Microsoft Excel. So I've set up this graph here. This is called a titration curve. It's going to show us the volume of sodium hydroxide that we've added, and on the x-axis, and then on the y-axis, that's going to have the pH. So we're going to use the knowledge that we have about acids and bases in order to calculate the pH at several points along the way of this titration. We're going to plot our points on this graph here, and we're going to see what the overall shape of the titration curve looks like. So obviously our calculation technique is going to be different depending on which part of the titration that we're in, but we will sort of cross that bridge when we get to it. We're gonna learn by doing, as they say. So the first thing that I want to calculate here, and this is very typical with titration type problems, is the volume of sodium hydroxide that is required to reach the equivalence point. So let me write that down. So volume of sodium hydroxide required to reach the, I'll just call it EQ point, right? And remember, the equivalence point, that's the point during the titration at which the number of moles of acid is equal to the number of moles of base. Now, in this particular problem, you can probably figure out what it is quite easily, but I think it's important to go through the motions of how to properly calculate this because the numbers won't always be so easy. And it's important to be able to figure out how to do it, right? So again, equivalence point, that's the point at which the number of moles of acid is equal to the number of moles of base. And so that means we need to convert what we have to moles, right? So we have 100 milliliters of our HCl solution. So I'll go ahead and write that out. So we have 100 milliliters of HCl, right? And we need to somehow convert that into moles of HCl. Well, we know that 1 molar means 1 mole per liter, right? Molarity is moles of solute per liter of solution. And so this 100 milliliters that we have to convert that into liters in order to be compatible with this molarity over here so that we convert to moles. So if we have 100 milliliters of HCl, I'll set up a quick little conversion factor in here in which we put milliliters on the bottom, we put liters of HCl on the top. Of course, there are 1,000 milliliters in 1 liter. And now that we've got liters, we can simply convert to moles using the molarity of the HCl solution. We'll put liters on the bottom and we'll put moles on top. If we have a 1 molar solution, that means that we have 1 mole per liter per 1 liter of solution here. Just going to make sure that all of our units cancel out here. Milliliters cancel with milliliters, liters cancel with liters, and we're left with moles. And so we have 100 divided by 1,000. Pretty easy calculation, mathematically speaking. That's going to be 0.1 moles. Try that again. That's a weird looking M. 0.1 moles of HCl, right? So if we have 0.1 moles of HCl, and the equivalence point is the point at which the number of moles of base is equal to the number of moles of acid, that means that we're going to need 0.1 moles of sodium hydroxide, right? Because that's equal to 0.1 moles of hydrochloric acid. You understand, right? So that's how much we need. So given that our concentration of sodium hydroxide is 1 molar, right? What volume of that solution do we need to equate to 0.1 moles of sodium hydroxide? Well, if we have 0.1 moles, we can convert that into liters quite easily using that molarity, right? So we're going to set up our conversion factor where we put moles on the bottom and we're going to put liters on the top, right? So if we have a 1 molar solution, that means we have 1 mole of sodium hydroxide for every 1 liter of sodium hydroxide. And just to keep our units consistent, we start out with milliliters of HCl, so I'll do it in milliliters of sodium hydroxide. I'll go ahead and convert this into milliliters, right? We'll put liters on the bottom, milliliters on the top, so we have 1,000 milliliters for every 1 liter. I'm going to go ahead and make sure our units cancel. Moles cancels with moles, liters cancels with liters, and our answer, 0.1 times 1,000, is 100 milliliters of sodium hydroxide. So what we just calculated is the volume of our titrant, the volume of our sodium hydroxide that is required to reach the equivalence point whenever we start out with a 100 milliliter, 1 molar solution of HCl, titrating it with 1 molar sodium hydroxide. So what I'm going to do is I'm going to jump into Excel real quick, and I'm going to highlight this cell right here, this row right here. So again, what we're doing is we're calculating the pH of several points along the way in this titration curve. So we know that 100 milliliters, that's going to be our equivalence point, right? And so we'll sort of bookmark that and sort of save it for later as we go forward. So, okay. So now we've figured out the volume required to reach our equivalence point. Now what we're going to do is trying to find a way to erase all this stuff very quickly. I think I can do it. Yeah. I don't really need any of this stuff anymore, so I'm going to just delete it. All right. So now what we're going to do is we're going to, like I said, we're going to calculate the pH upon adding various amounts of sodium hydroxide. So starting with 0 milliliters. So initially, before we add any titrant at all, what is the pH of this solution? Well, this is pretty straightforward, especially if you have a solid understanding of acids and bases, right? It's simply going to be the pH of a 1 molar solution of HCl, right? Now, HCl, of course, being a strong acid, means that all of that HCl is going to be converted into hydronium ion and water, right? And so that means that if we have 1 molar HCl, then we have 1 molar hydronium ion. So the concentration of hydronium ion, H3O+, is going to be equal to 1 molar, right? And we also know, or at least we should, that the pH is equal to the negative log of the hydronium ion concentration, negative log of the concentration of H3O plus. In this case, that concentration of H3O plus is 1 molar, right? And so the negative log of 1, type that into your calculator, you're going to get a value of 0. So initially, our pH, before we even add any sodium hydroxide at all, is 0. So I'm going to hop into Excel real quick. I'm just going to populate this cell right here with a 0. So that's going to plot our first point on the titration curve, which is right here, 0 milliliters of sodium hydroxide added, and excuse me, 0 pH, right? So now it's going to get a little bit interesting. So what we're going to do is, I think what I'd like to do is, whoops, I'm just going to get rid of all this stuff, is I'm going to, let's say I'll put this in green. Actually, I'll do it in blue. So I'll just include a little row up here that says volume of sodium hydroxide added, right? And then I'll just keep that up there, and I'll just change the number every time we want to go to another volume, right? So the first one that we're going to do is 10 milliliters. So what is going to be the pH upon adding 10 milliliters of our 1 molar sodium hydroxide? So I'll go ahead and write that in, 10 milliliters, right? So what we need to do here is we need to figure out how much sodium hydroxide is added in moles, right? So when in doubt, convert to moles, right? So if we have 10 milliliters of our sodium hydroxide, right, and convert that into liters simply by understanding that there are 1,000 milliliters in 1 liter, right? Now that it's in liters, we can use the molarity. So we have 1 liter on the bottom, 1 mole on top. That's what a 1 molar solution means, right? You have 1 mole per liter, making sure that our units cancel, milliliters cancel, liters cancel, and we are left with 10 divided by 1,000, which is 0.01 moles of NaOH, right? Now, earlier, we figured out how many moles of HCl we initially have. Anybody remember what that was? That happened to be what? That was 0.1 moles of HCl, right? So if I have 100 milliliters of 1 molar HCl, that's 0.1 moles of HCl. And now what we can do is we can set up a little table like we've done previously. Whenever we were doing the stoichiometry calculation of when you add an acid or a base to a buffer solution, there's that stoichiometry part of the calculation. So we're going to do something similar to that here, right? So what I'm going to do is I'm going to write the neutralization equation for this chemical reaction. So there's the OH minus ion that we add, right? That's the hydroxide. And then we have the hydronium ion that's already in there, and they react, they neutralize one another to form water, right? And so I'll set up 3 rows here, one in which we have the conditions before the addition of the hydroxide, the addition itself, and then what the conditions are after the addition, right? So before the addition, we have essentially 0 moles of hydroxide. We do have some hydroxide in there due to the auto-ionization of water. Anytime you have any aqueous solution, you're going to have a little bit of hydroxide in there because water will ionize on its own, but that amount is negligible, very, very small compared to the amount of hydroxide that we're going to add. So we can assume that this is approximately 0 moles of hydroxide ion initially. And then we figured out earlier that initially we have 0.1 moles of hydronium ion, right? Now, our addition, what did we add? Well, we added 0.01 moles of sodium hydroxide. So that means we added 0.01 moles of hydroxide ion, right? All of that added hydroxide is going to be neutralized by the hydronium because we have an excess of it. We have more than enough hydronium ion to react with all of the hydroxide ion that we add. And so afterwards, we're going to have approximately 0 moles of hydroxide, but the amount of hydronium is going to be reduced by the amount of hydroxide that we added. So it's going to be 0.1 moles minus 0.01 moles. And so our new amount of hydronium then becomes 0.09 moles, right? We have 0.09 moles of hydronium ion in this solution, right? And so we need to be able to convert that into a concentration. So we have moles, but we need concentration in order to be able to do the calculation for pH, right? So the concentration of H3O plus is going to be the amount of H3O plus in moles, so that's 0.09 moles divided by the total volume. And this is very important that we understand that the total volume is not only the initial volume of HCl that we started with, but also added to that the amount or the volume of sodium hydroxide that we added. So we started out with 100 milliliters, we added 10 milliliters to it, so our total volume is then going to be 110 milliliters, which is 0.11 liters. And I converted that to liters in my head just now because I understand that molarity is moles per liter, so our volume has to be in liters in order to get a molar concentration. And so I'm going to put this into my calculator real quick. So we have 0.09 moles divided by 0.11 liters, so that's 0.09 divided by 0.11, so not 11.11, and that ends up being, I'll just do it to 3 decimal places, 0.818 molar, right? So that's what our concentration of hydronium ion is. It is 0.818 molar. And now simply in order to calculate the pH of this thing, all we need to do is to take the negative logarithm of that hydronium ion concentration, in this case negative logarithm of 0.818 molar. And what does that end up being? Well, I don't know. I'm doing this for the first time. Let me punch this into my calculator real quick. By the way, I hope you brought your scientific calculator because I would highly encourage you to follow along with me as I'm doing these, because it's entirely possible that I make a calculation error or other mistake. So I'm sort of hoping and relying on you to sort of keep me in check, make sure I'm doing these things correctly, because even chemistry experts are human. We do make mistakes. All right, so negative logarithm of 0.818, that ends up being 0.087. 0.087. So I'm going to go back into Excel, and I'm going to plot this point here. So when we added 10 mils of the sodium hydroxide, we ended up with 0.087. So that gives us the second point on our titration curve. So it looks kind of steep right now, but we'll see as we do this that this isn't exactly a steep change in pH from the initial pH to the pH upon adding 10 mils of sodium hydroxide. But if you want to see what the overall pH curve looks like when we're done, stay tuned. And by the way, smash that like button if you haven't already. I would wholeheartedly appreciate that. And consider sending a super chat if you really want to show your love. All right, we're going to go back to the whiteboard real quick. So the next volume of sodium hydroxide that we are going to add here is going to be, let me erase all this stuff down here. We no longer need it. Erase that. So the next volume that we're going to add here is 20 milliliters. So we're going to calculate the pH upon adding 20 milliliters of sodium hydroxide, of 1 molar sodium hydroxide to this 100 milliliter sample of 1 molar HCl, right? So the moles of NaOH have now changed. What else has changed? Well, the moles of HCl hasn't really changed, at least initially. I'm just trying to be mindful of what I erase so I don't have to like reinvent the wheel and do the entire calculation all over again. Trying to save some time here. By the way, if you're watching this as a video later on, you might want to consider changing the speed to like 1.5 speed or double speed or something like that. Like I said, I'm doing something I've never done before by using Excel and jumping back and forth between the whiteboard and Excel. So I expect this to be a little clunky and not super tight and seamless from one moment to the next. Probably not going to have a whole lot of continuity. So maybe turn up the speed. And if you're watching this live, thank you for your patience. I highly appreciate it. Okay, so 20 milliliters of NaOH. What is that going to look like? Well, 20 milliliters of NaOH we need to figure out what that is in moles, right? So we're going to do this calculation again, but this time with 20 milliliters. So if we start out with 20 milliliters of NaOH, we're going to convert that into liters, right? So milliliters on the bottom, liters on the top. There are 1,000 milliliters in 1 liter. Now that we have liters, we can convert that into moles using the molarity. Liters on the bottom, moles on top. 1 molar means there's 1 mole for every 1 liter. Units are going to cancel. Milliliters, milliliters, liters, liters. And we end up with 20 divided by 1,000, which is 0.02. I think I got that correct. Yeah, 0.02 moles of NaOH, right? So let me take that 0.02, drag it up there. So we have 0.1 moles of HCl, 0.02 moles of NaOH. Obviously, our HCl is in excess, so all of that added sodium hydroxide is going to be neutralized. So the addition in this case is 0.02 moles of hydroxide. So that's all going to be neutralized, leaving us with the original amount of hydronia minus that 0.02 moles. So if we have 0.1 and we subtract 0.02 moles away from that, what do we end up with? We end up with 0.08 moles of hydronium ion, right? Now we need to get that into a volume. We need to convert that 0.08 moles into a volume, not into a volume, but into a concentration by dividing by the total volume, right? So we have concentration of hydronium ion, right? It's going to be equal to the amount of it in moles, which is 0.08 moles, divided by the total volume. Got to be careful here because the total volume is the original 100 mils that we had, and also the added 20 milliliters, right? That ends up being 0.12 liters, 120 milliliters, 0.12 liters. By the way, if I'm leaving anybody in the dust, please let me know and I can slow down. JL says, I wish I paid attention more to math in school. Thanks, JL, for joining. I really appreciate your being here. And, well, I mean, you know, my advice would be don't waste time with regret, right? It's in the past. You can't really do anything about that. All we can do is, all we can change is the present and the future. We can't really do much about the past. So, and if there's, again, if there's anything that I'm confusing anybody on, please let me know. And I'd be happy to help. Demeen says, we have a quiz on this tomorrow. I'm so lucky right now. Hey, cool. Wow. Good timing then, huh? Very cool. All right. So that goes double for you. If I'm saying anything that's confusing or if I'm working too fast, please just let me know. So, all right. So let me just recap what we did here. So we had 20 milliliters of sodium hydroxide. We converted that into moles, right? And then we set up this little table here that shows us the conditions of the solution before the addition, what the addition is, and after the addition, right? Before the addition, we had 0.1 moles of hydronium ion. The addition was 0.02 moles of hydroxide ion, right? All that hydroxide gets neutralized because the hydronium is in excess, so we end up with 0.08 moles of hydronium ion, and now we need to divide that by the total volume to get the molar concentration, the molarity of the hydronium ion. So we end up with 0.08 over 0.12. I'm going to calculate that real quick. 0.08 divided by 0.12, and that is 0.667 molar, right? 0.667 molar. That's what our hydronium ion concentration is. And then the pH, of course, is, yep, you guessed it, pH is the negative logarithm of the hydronium ion concentration, so negative logarithm of 0.667 molar. And that turns out to be, I don't know yet because I haven't calculated it yet, negative logarithm of 0.667 molar. Excuse me. Oh, man, I have way too much stream left in the night to be already losing my voice. This is not good. All right, negative log of 0.667 molar is 0.176. And look at that. I got some participation from the mean over there. Thank you for participating. Both of us got the same thing, so I'm sure we did it right. All right, so 0.176. So I'm going to hop back into Excel and populate this cell right here with 0.176. And so our titration curve is sort of starting to take its shape, but we'll really have a better idea when it's all done and over with. All right, so the next volume that we're going to look at is 40 milliliters of added sodium hydroxide. So I'm going to climb back into the whiteboard here, and I'm going to erase all of the stuff that I no longer need or that is no longer relevant to this particular part of the problem here. So we're going to do, so we did 20 last time, we're going to do 40 milliliters of added sodium hydroxide. So 40 milliliters of sodium hydroxide, concentration of it is 1 molar. What is the amount of that in moles? That's where we have to start the calculations, by converting that into moles. And it might seem redundant at this point, but I'm going to do it yet again because repetition is the key to success. So we have 40 milliliters of the sodium hydroxide, right? There are 1,000 milliliters in a liter, right? So we have 1 liter and we have 1,000 milliliters. And again, the reason why we convert it to milliliters is because molarity is moles per liter. So we have to convert our volume to liters in order to use molarity to convert to moles. And since it's a 1 molar solution, that means that for every 1 liter, we have 1 mole of sodium hydroxide. Gonna make sure my units cancel, and it looks like they do. And so we end up with 0.04 moles of sodium hydroxide. So I'll take this 0.04 and just kind of drag it up there, right? As for the rest of this, I think I can just delete it because I no longer need it. Whoops, I'm gonna erase the rest of that too. Okay, very cool. All right, so we have 0.04 moles of sodium hydroxide, 0.1 moles of HCl. And again, that 0.1 moles of HCl, all that is just taking 100 milliliters and converting it to liters and then converting it to moles using the 1 molar. And I did that at the very beginning. I just don't feel like I need to do it again because we've already done it once before. Okay, so in this case, we start out with 0.1 moles of hydronium ion. We add 0.04 moles of hydroxide ion, right? It's all going to get neutralized because the hydronium ion is in excess. That won't always be the case, but in this case, we have much less hydroxide than we do hydronium ion. So 0.1 minus 0.04, that ends up being 0.06 moles of the hydronium ion. And of course, we need to convert the amount of hydronium ion in moles into a concentration of hydronium ion by dividing by the total volume. So we have 0.06 moles of H3O plus divided by the total volume. What is our total volume? Well, it's going to be the 100 milliliters that we started with plus the 40 milliliters of solution that we added for a total of 140 milliliters, which is 0.14 liters, right? So 0.06 moles divided by 0.14 liters. That ends up being, what is it? So 0.06 moles divided by 0.14 liters. Value that I got for the concentration of hydronium ion is 0.429 molar, right? 0.429 molar. Gonna drag that right over there. And then the pH, of course, is going to be the negative log of the hydronium ion concentration, negative log of 0.429 molar. Gonna calculate that real quick. Negative log of 0.429. And I got a value of 0.368. 0.368. I'm going to go ahead and throw that into Excel right now, so 0.368. That's the pH when we added 40 milliliters of 1 molar sodium hydroxide to our 100 milliliters of 1 molar HCl. So now we're going to move on and we're going to do 80 milliliters. So what happens? What's the pH going to be when we add 80 milliliters of that 1 molar sodium hydroxide solution to our 100 milliliters of 1 molar hydrochloric acid solution? So once again, I'm just going to erase everything that I don't need here, everything that is no longer relevant. Okay. All right, so instead of 40 milliliters, we're now going to do 80 milliliters. So just as we did in the last example, we're going to convert our 80 milliliters of sodium hydroxide into moles, right? So we have 80 milliliters of sodium hydroxide. Going to convert that volume into liters, milliliters on the bottom, liters on the top. Of course, there are 1,000 milliliters in a liter. And now that we have liters, we can convert that into moles using the molarity concentration of that sodium hydroxide, which is 1 molar. So we have 1 mole for every 1 liter. Going to make sure my units cancel out, and they do. And so we have 80 divided by 1,000, that's 0.08 moles of sodium hydroxide, right? 0.08 moles of sodium hydroxide. So I'll just drag that right up there where it belongs. Delete the rest of that because we no longer need it. Like it didn't all get deleted. There we go. All right. So in this case, our addition is 0.08 moles of the hydroxide ion, right? So the hydronium ion is still in excess, although not by much, but still enough to neutralize all of the added hydroxide ion in here. So that means that our hydroxide is going to go away, and our hydronium ion concentration will become 0.1 minus 0.08, which is 0.02 moles. So that is our amount of hydronium ion. But of course, we need to get the molar concentration of hydronium ion by taking that 0.02 moles and dividing by the total volume. In this case, the total volume is going to be 180 milliliters. We started out with 100 and we added 80, so that's 180 milliliters, which is equal to 0.18 liters. So our hydronium ion concentration then becomes 0.02 divided by 0.18, 0.111 molar. So our hydronium ion concentration is 0.111 molar. And then, of course, to get pH, we just take the negative log of the hydronium ion concentration, negative log of 0.111. And what is that? I will tell you as soon as I calculate it. Negative log of 0.111. And that is 0.955. That's what I got. And again, feel free to correct me if I am wrong. I'm pretty sure that's correct. 0.955. So I'm going to hop back into Excel and punch this into this cell right here. 80 milliliters, 0.955. Okay, here. So we see that the pH curve is sort of starting to take its shape. So it seems like it's accelerating a little bit. We're sort of in the point at the titration where adding a relatively small amount of our titrant, of our base, is resulting in a fairly large portion or a fairly large change in pH. And this is something that sort of tips us off that we're getting pretty close to our equivalence point here. So, all right, now we're going to calculate the pH upon adding 100 milliliters of our 1 molar sodium hydroxide to our 100 milliliters of 1 molar hydrochloric acid, right? Now, earlier, we established that 100 milliliters, this is the volume required to reach the equivalence point. So what we're going to do is we're going to calculate the pH of this solution at the equivalence point, right? So let's go back to the whiteboard. Now this is going to be, we're kind of going to have to dig back into our memory banks and understand the theory of acid-base chemistry in order to understand this. So let me just go ahead and do what we did last time. So I'm just going to erase everything that no longer applies here. So I erase that. Ooh, my stuff's kind of lagging a little bit. I don't know what's going on. Okay. So just bear with me while I erase all of this stuff that no longer means anything. So now we're looking at 100 milliliters. So what's the pH going to be when we add 100 milliliters of 1 molar sodium hydroxide to our 100 milliliter sample of 1 molar hydrochloric acid? Whew, that was a mouthful. No wonder I'm losing my voice so fast. Anyway, all right. So do the same thing we did before, right? Start out with 100 milliliters of NaOH. We're going to convert that into liters, of course. Milliliters on the bottom, liters on the top. There are 1,000 milliliters in 1 liter. Then we can convert that into moles using molarity. Liters on the bottom, moles on the top. 1 mole per liter. That's what a 1 molar solution means. Milliliters cancel, liters cancel. And so we have 100 divided by 1,000, and that's 0.1 moles of NaOH. And again, this is kind of a little bit redundant because we already sort of established this before, that this is the equivalence point. So this is the point at which we have equal amounts of acid and base. So it makes sense that our amount of sodium hydroxide in moles is 0.1 moles, because that's what the term equivalence point means in the event of a titration, right? So if we set it up here, if we look at our table right here, so notice that, okay, so our addition of sodium hydroxide in this case is 0.1 moles, right? So this looks like the amount of hydroxide ion is now just enough to neutralize all of our existing hydronium ion, to the point where after the addition, we're left with approximately 0 moles of H3O plus, right? So how on earth are we going to calculate the pH of this solution where there's like a zero, like there's no concentration of hydronium ion? Well, you might think that the concentration of hydronium ion in this case is 0 molar, but it's really not 0 molar. And in order to understand this, we kind of have to dig back into our memory banks, as I said previously, and understand a little concept called the auto-ionization of water. So a sample of water on its own, assuming you're at 25 degrees Celsius, and I probably should have mentioned that from the beginning, is that we're going to assume this is at 25 degrees Celsius because that's the most commonly reported temperature in chemistry textbooks when you're talking about acid-base chemistry, right? So Otto, that's my dog's name actually, water will ionize on its own according to this equation where you have a water molecule and another water molecule reacting reversibly, right? These are supposed to be equilibrium arrows. Let me try that again. To form, there we go, that's a little bit better. To form hydronium ion and hydroxide ion, right? This happens on its own. You don't need to add any additional acid or base in order to get water to do this, right? And the equilibrium constant associated with this process, right? And this is called Kw. This is called the ion product constant for water, right? Because this is an equilibrium reaction, it can be represented by an equilibrium constant. Now, water is a pure liquid, right? So pure liquids always get omitted from the equilibrium constant expression, right? But hydronium and hydroxide, those are aqueous, so they're going to be in the equilibrium constant expression, right? So anyway, excuse me, the equilibrium constant looks like this, where we have concentration of H3O plus times the concentration of OH minus, right? So it's products over reactants. Again, our reactants don't show up in the equilibrium constant expression, but our products do because they are aqueous, right? Now Kw, right, which is equal to the product of hydronium and hydroxide ion at 25 degrees Celsius has a value of 1.0 times 10 to the minus 14, right? 1.0 times 10 to the minus 14, right? And let me just erase this equation real quick just so that I can, whoops, didn't mean to do all that. I'm going to erase this equation right here just so I can give myself a little bit more room, right? So now we know that the amounts of hydroxide ion and hydronium ion are equal, right, in a neutral sample of water, right? So that means that if the hydroxide ion concentration is equal to the hydronium ion concentration, then we can rewrite this as the concentration of hydronium ion squared is equal to this 1.0 times 10 to the minus 14. And so if we want to get the concentration of hydronium, click out of this, I don't know what's on here. If we want to get the concentration of hydronium, right, that's simply going to be the square root of 1.0 times 10 to the minus 14, which is equal to 1.0 times 10 to the minus 7. And then to get pH, we're going to take the negative logarithm of 1.0 times 10 to the minus 7, which is equal to 7. So again, this is assuming you're at 25 degrees Celsius. And you probably know and have an intuitive idea of this already, that at 25 degrees Celsius, a neutral pH is 7. And that's why. 7 is not just some random number that came out of nowhere. The number 7 comes from the fact that the Kw, the ion product constant for water, as a result of the ionization of water, is 1.0 times 10 to the minus 14 at 25 degrees Celsius. You take the square root of that, you get 1.0 times 10 to the minus 7. You take the negative log of that, and you get 7, right? So whenever you have a strong acid, strong base titration, the pH at the equivalence point will always be equal to 7. And I know I took a very long time to explain that, but that's only because I really want to make sure that we have the theory very well understood. So let me look at some messages in the chat. It says, question, do you have to do the same step when it's a weak acid, strong base, or vice versa? I don't know what you mean by the same step, but for a weak acid, well, I want to do this next week. I want to do the weak acid, strong base titration next week, and we'll take a look at that, like how to calculate the pH of a weak acid, strong base titration when you're at the equivalence point. It's basically like an equilibrium type problem where you have like a concentration of weak acid, and you do your like your ice table and your quadratic equation. Maybe you invoke the X's small approximation, all that stuff. If all that stuff sounds foreign to you, then I would suggest watching my chemical equilibrium playlist or my acids and bases playlist, and that'll bring you up to speed on that stuff. Or if you don't feel like doing any of that, just stay tuned next week, because we'll do a weak acid, strong base titration next week. But very good question, though. I'm glad you asked it, because we are definitely going to address that going forward. So, all right. So now that we've established that in a strong acid, strong base titration, the pH at equivalence point is always going to be 7. Now we can hop back into Excel here and type in 7 for our pH value at the equivalence point. Now notice this. Notice that our pH curve, our titration curve, has shot way up, right? And this is something I was talking about earlier, right? Where the closer you are to the equivalence point, the more dramatic the change is, right? Small amounts of added base result in very large changes in pH when you're close to that equivalence point. All right, so we're going to move forward. We got a couple of more of these things to calculate before we call it a night. And we're going to do 110 milliliters. So that's our next volume of sodium hydroxide that we're going to look at here. So I have lost my window here. Okay, here we are. So let me just erase all of this stuff that no longer is of value to us. So I'm gonna erase that. I'm gonna erase that. And I'm going to erase that. Now we're doing 110 milliliters of sodium hydroxide, right? So 110 milliliters of sodium hydroxide, right? Going to convert that into liters. Liters on the top and the liters on the bottom. 1,000 milliliters are in liter. And then it's a 1 molar solution, right? So we end up getting moles on the top, liters on the bottom, 1 mole per liter. We've done this calculation a bunch of times already, but like I said, I think repetition is the key to success, so we're going to just keep doing it. Doesn't hurt to keep doing it. All right, so we end up with 110 over 1,000, which is equal to 0.11 moles of sodium hydroxide. So I'm going to take that 0.11, whoops, going to take that 0.11 value here. I'm going to drag it up there so we can keep that in mind. I'm going to do away with the rest of that stuff because we no longer need it. JL says, over how much time will each change be measured? I'm not sure what you're talking. I mean, the reaction is pretty fast. I guess it just really depends on how quick you are with your stopcock, like how quick you're opening that stopcock. I mean, generally speaking, you want to, do it 1 drop at a time so that you're carefully adding the amount of base that you want in there. You're not adding too much. You might overshoot your equivalence point and then have to do the titration all over again, which might be difficult, especially if you have like a limited amount of sample. Like if you only have like 1 sample and you're trying to titrate it, you want to make sure that you're treating it very, very carefully. Like don't rush, clear your schedule. Whatever's on your schedule for the rest of the day, just cancel it and just focus on that titration if you want to make sure you get it right. Okay, so we have 0.11 moles of sodium hydroxide, 0.1 moles of our HCl, right? So our addition in this case is 0.11 moles of hydroxide ion. So now we're in a position where the amount of hydroxide that we're adding is actually greater than our existing amount of hydronium ion. So in this case, all of our hydronium ion is going to be neutralized. So we're going to end up with approximately 0 moles of hydronium, right? So the question then becomes, how much hydroxide do we end up with? Well, it's going to be 0.11 moles minus 0.1 mole, and that ends up being 0.01 moles, right? So we have 0.01 moles of hydroxide ion, and we have virtually no hydronium ion, right? So now what we need to do is we need to take that 0.01 moles, and we need to convert it into a molar concentration of hydroxide. Molar concentration of hydroxide by dividing that 0.01 moles by the total volume. So our total volume in this case is 100 milliliters plus 110 milliliters, which is going to be 0.21 liters. 210 milliliters, just converted into liters in my head. So 0.01 divided by 0.21, what is that? So I'm going to calculate that real quick in my calculator, and I would encourage all of you to do the same with your scientific calculators. 0.01 divided by 0.21, what is that? That is 0.0476 molar, right? So that's our concentration of hydroxide ion, right? 0.0476 molar, right? Now we can't calculate pH directly from this, but one thing we can do is we can calculate the pOH, right? So we know, at least we should know, that the pOH is equal to the negative log of the hydroxide ion concentration. And one thing that we should also know is that the sum of pOH and pH is equal to 14. And again, that's at 25 degrees Celsius. So we can use these two relationships to get pH, right? We can calculate pOH, right? And then we can subtract that pOH from 14 to get our pH, right? So negative log of concentration of hydroxide ion, that's going to be negative log of what? It's going to be negative log of what we just calculated, which is 0.0476 molar. And that ends up being what value? So the mean says it's 1.3. I'm just going to double check that if you don't mind. 0.0476. So what did you say? 1.3. So yeah, I'll do it to 3 decimal places. 1.322 is what I got. So yeah, if you were just rounding to the 10th place, yeah, 1.3, that's correct. Good job, Demeen. You are on fire tonight. I think you're going to crush your exam tomorrow, and I know we're all in the live stream pulling for you. Everybody else who's watching, please show Demeen some love that he's going to crush his exam. Or not his exam, but his quiz tomorrow. I just read it a second ago. He says, Demeen says maybe. Nah, you gotta remove that maybe word from your vocabulary, man. Not maybe, definitely. You're going to spank that quiz. All right. So JL says, good luck. Right on, man. We should all be encouraging each other. Positive vibes. Okay, so now we can simply calculate pH, right? pH is going to be 14 minus that 1.322, and that's equal to 14 minus 1.322. And I got a value of 12.678. 12.678. So I'm going to hop back into Excel real quick and type that in. 12.678. Not 687, 678. Okay, so got a steep pH curve now. So we got 3 more volumes of added sodium hydroxide to go before we're done. The next one is 120 milliliters. So we're going to move on and do that. Let's see. So 120 milliliters. Okay. So I'm going to erase everything that no longer applies. Erase that. Okay. Let's see. All right. So I think I'm going to run through these calculations a little bit more quickly. Do some more math in my head here because we've done these calculations over and over and over again. Let me change this real quick. So instead of 110 milliliters, it's now 120 milliliters, right? So 120 milliliters of 1 molar sodium hydroxide. I'm just going to do the math in my head. That equates to how many moles of sodium hydroxide, right? 120 milliliters, 1 molar. That ends up being what? 120 divided by 1,000, so that's 0.12 moles of sodium hydroxide. And again, if this seems like I'm going too fast, just either tell me to slow down or just kind of rewind back earlier in the video where I sort of did these calculations more thoroughly. So anyway, all right. So we have 0.1 moles of hydronium initially. We're adding 0.12 moles of hydroxide, right? So our hydroxide is in excess. That means we end up with virtually no hydronium ion. All of it gets neutralized by our hydroxide. So that 0.12, it's going to be reduced by 0.1. So we're going to be left with 0.02 moles of the hydroxide ion, right? And so to get the concentration of hydroxide, we're going to take that 0.02 moles of it, and we're going to divide that by the total volume. In this case, that's 100 milliliters plus 120 milliliters, which is 0.22 liters, or 220 milliliters. I just converted that in my head, as I've been doing over and over again throughout this presentation. So we're going to calculate that concentration. So that's 0.02 divided by 0.22. That ends up being 0.0909 molar, right? So that's what our concentration of hydroxide is. 0.0909 molar, right? And then we can get POH from that. That's going to be the negative log of 0.0909, which is, let's see, negative logarithm of 0.0909. And I got 1.041. So that's POH. And then to get pH, it's going to be 14 minus 1.041, which is equal to 15 minus 1.041, which is equal to 12.959. Demeen says 12.68. Oh, that was from earlier. Okay, I was like, oh no, did I mess up? Entirely possible, folks. But I think that was a chat message from earlier when I was doing the previous one with 110 milliliters of added sodium hydroxide. Anyway, all right, so 12.959. That is our pH value. Demeen says no, that was from earlier. Yeah, that's what I thought. It just clicked into my brain that was from earlier. So my apologies. All right, so we have 12.959. So I'm going to plug that into this cell right here. 12.959. Okay, so now we see that once we are significantly beyond our equivalence point, now our titration curve is starting to level off again. So it's only like when you're close to that equivalence point do you have that like dramatic change effect where a small amount of added base is going to result in a large change of pH. It seems like we're well past that. But just to make sure this isn't a fluke, let's go ahead and do the last two examples here before it's all wrapped up. What do you guys think? See, all right. So the next volume that we're going to look at is 140 milliliters. So I'm going to just erase all this junk. I mean, if you do these kind of calculations over and over and over again, like I'm doing right now, like you're going to be so proficient at them that you'll practically be able to do it like blindfolded with your hands tied behind your back, and you'll be really good to go on test day. So this is, being interactive, like getting your hands dirty, like doing these calculations by hand. Very, very important to really enhance your understanding of this content to the point where it becomes second nature to you. Okay, so I'm going to erase all this stuff. Let's see. Erase you. Okay, so what did we say? We said 140, right? 140 milliliters. That's our next point in our titration curve that we're going to look at. So 140 milliliters, it's a 1 molar sodium hydroxide solution. So just to do the math in my head real quick, that ends up being 0.14 moles of sodium hydroxide, right? So that's how much we're adding here, 0.14 moles of sodium hydroxide. So 0.14 moles of hydroxide ion, right? Since our hydroxide ion is in excess, there's more of it than there is hydronium. It's going to neutralize all of our hydronium, leaving us with virtually no hydronium ion, and 0.14 minus 0.1, or 0.04 moles of hydroxide, right? That's our amount of hydroxide. So to get the concentration, we're simply going to take that 0.04 moles of hydroxide, divide that by the total volume. Total volume in this case, 100 milliliters plus 140 milliliters. So that's going to be 0.24 liters, right? So yeah, 240 milliliters converted to liters, 0.24 liters. And that ends up being, let's see, 0.04 divided by 0.24. What I got was a volume, not a volume, but a concentration of 0.167 molar. 0.167 molar. That is our concentration of hydroxide ion. From there, we're going to calculate pOH by taking the negative log of 0.167, and that becomes what? So yeah, Demeen says 0.167. Yes, we're doing this correctly. Good. Okay, so negative log of 0.17, that ends up being 0.777. I mean, you said 0.778. I'm not sure who's rounding incorrectly here. I got 0.777. It's like 0.7772, whatever. Anyway, it's probably not that big a deal, but I'm just going to stick with that. 0.777. And so, of course, to get pH, we're going to take 14 and subtract from 14 our pOH, which is 0.777. And that's going to be equal to 15 minus 777. is equal to 13.223. So that is our pH. So I'm going to go back into my spreadsheet here, and I already forgot it. 13.223. Okay, there it is. 13.223. Okay, so it definitely seems like our pH curve has sort of leveled off at this point. And then we'll just go ahead and do one more point of this titration curve, and then we will be done building this titration curve. So I'm excited about that. I'm excited about being done. All right. So let's see. I got another message that says, yeah, you're right. You're correct. Okay. So let me go ahead and just erase all this stuff one more time. So we are at the home stretch here, folks. We are very, very close to being completely done building this titration curve. All right, so we're going to look at 180 milliliters of added, do that a little bit better, 180 milliliters of added sodium hydroxide. So 180 milliliters, 1 molar NaOH, that equates to 0.18 moles of sodium hydroxide. And again, if you're joining the stream a little late, if that calculation is confusing to you, there's been several examples previously, earlier on in this stream, where I've done this in a more thorough manner, where I do all my conversion factors and all that stuff. So we're going to set this up here. So 0.18 moles of hydroxide is what I add to this. Of course, since it is in excess, it's going to neutralize all of our hydronium, leaving us with virtually no hydronium ion, and 0.18 minus 0.1, which is 0.08 moles of hydroxide. That's our amount of hydroxide. But of course, we need to convert that into a concentration by dividing by the total volume. So the concentration of OH minus is going to become 0.08 moles divided by total volume, 100 plus 180. That's 280, or 0.28 liters. Let's see. So we have 0.08 divided by 0.28. That ends up being 0.286 molar. So that is our concentration of hydronium ion, 0.286 molar. Dale says, what would you recommend to watch to get a better understanding of this? My next stream, it'll be next week. Or my previous content, like my chemical equilibrium playlist, or my acids and bases playlist, or the earlier videos in my Aqueous Ionic Equilibrium playlist. But other than what I provide, I'm sure there's a lot of stuff out there that can help with this. And send me an email. Like, you can find my email by going to my channel page. Send me an email to remind me about it, and I can see what I can dig up. And I can try to find you some resources to help you out. So I'd be happy to help, even if that means not watching my stuff. I don't really care if you watch my stuff or not. I just want you to understand the content better. All right, so that's our concentration of hydroxide. We can calculate pOH from that by taking the negative log of the concentration of OH, which is 0.286. So the pOH ends up being, let's see, negative logarithm of 0.286. That ends up being 0.544. And then finally, we can get pH by taking 14 and subtracting our pOH from 14. So it's 14 minus 0.544, which is equal to 14 minus 0.544. That is equal to 13.456. 13.456. JL says, I will search through your playlist. Yeah, one thing about my playlist is, like, my live stream videos, what I'm trying to do is I'm trying to, like, include timestamps in the videos, like chapters within the videos, so that you can look on the timeline, and whatever part is, like, relevant to what you want to watch, like, you can just click on that timestamp and it'll just jump straight ahead to that part. So, like, when you're watching these videos, like, check the descriptions, because you might be able to you know, you probably don't want to watch the entire live stream, you just want to watch the part that you're interested in. So look for the timestamps in the description. You can just click and just jump to that point in the videos, and hopefully that'll save you some time. So, okay, we calculated that pH is 13.456. So we're going to finally put that into our curve here, 13.456. And there you have it, folks. There is our titration curve. Okay, so that, again, it's pH on the y-axis and the volume of added sodium hydroxide on the x-axis. So you see you have this like sort of S-shaped curve here where it gets really steep close to the equivalence point, and then it sort of levels off. The exact shape of the curve sort of depends on the strength of the acid, whether you have a strong acid or weak acid, or strong base or weak base. And like I said, in the next video, in the next live stream, we're going to do another titration problem where we look at titrating a weak acid with a strong base. The calculations are significantly more complicated. We're going to have to consider like the stoichiometry and equilibrium calculations associated with buffers, which is something that we saw earlier in this live stream series. How to calculate the pH of a buffer solution, how to calculate the change in pH associated with the disturbance of a buffer solution. So like all that stuff is going to come back, hopefully not to haunt us. Hopefully we'll be able to be prepared and equipped to solve these problems, but we're going to have to do that. We're going to have to use the Henderson Hasselbalch equation. So all that is gonna come back and going to be very, very relevant when we talk about weak acid, strong base titration. So a couple more messages. Damien just said, so my professor in the book we use for analytical didn't convert to milliliters to liters. So does that matter when you're trying to find the concentration? Yes, absolutely it matters. Yeah, because molarity is moles of solute per liters of solution. It's not moles of solute per milliliters of solution. So if you want to calculate pH, take the negative log of the concentration of hydronium. That concentration has to be in moles per liter. I mean, I guess it could also be in millimoles per milliliter because that's the same thing numerically as moles per liter. My personal preference is just convert everything to molarity. That makes things consistent, predictable, and easy. So that's just my my 2 cents on that one. All right, everybody. So that's going to be it for me. Thank you for joining me. Thank you for your participation to those of you who participated. I thought it was a pretty good, pretty productive stream. Of course, I'd love to hear your feedback. If you're watching this as a video, please feel free to leave feedback in the comments below. Thank you very much for watching for as long as you have. Really, really appreciate it. If you find the stream valuable, I would highly appreciate your leaving a thumbs up on the video. It goes a long way to help with discovery. Tune in for the next stream. We're going to be doing another titration type problem where we build a titration curve, but instead it's going to be more complicated because we're going to be doing a weak acid titrating with a strong base. So, all right, everybody. Thanks again. Love you guys, and I will talk to you soon. All right, take it easy.